All right, so this next section is on electrochemical cells. Basically, an electrochemical cell is changing chemical energy into electrical energy. So what you're doing, in essence, is making a battery. So these electrochemical cells, also called galvanic cells, were developed back in the late 1700s, and they really haven't changed that much in the last like 230-ish, 240 years. Um, Gotten a little bit more efficient and a little bit and smaller, obviously, but the principles are the same. You have one side's the anode and one side's a cathode. One side you're losing electrons, one side you're gaining electrons, and you're connecting the circuits with a wire and a salt bridge to electrodes suspended in solution. So what you'll need to know for electrochemical cells, here's our goals on the next page. So what you'll need to know, these are the goals, right? Construct an electrochemical cell, define and label the parts. So you have all the different parts and we'll go over them. Tell the half reactions, the one that's happening at the anode, one that's happening at the cathode. So it's oxidation and reduction. Direction and flow of each type of ion, the flow of electrons, determine the voltages of the half cells by combining them together, identified standard conditions for the electron potential cells, and predict the voltage that's being produced. So our definitions, we'll go through these guys. So electrochemical cell converts chemical energy into electrical energy. Electrode, this is a conductor, usually a metal, at which a half cell reaction, we have oxidation or reduction occurs. So our anode, this is an electrode, right, where the oxidation occurs. So it loses electrons at the anode. We actually lose mass at the anode as well. Our cathode, this is where a reduction reaction occurs. So we're gaining electrons, we're gaining mass at our cathode. Memory aid for deciding where they happen. So oxidation at the anode, so they're both vowels. Anode, you have oxidation. Cathode, reduction, both consonants. So maybe that might help you to memorize what's happening at which location. So here's a typical cell. So we have our anode. This is the oxidation reaction happening at the anode. We have our cathode. Here's a reduction happening at our cathode. This is called the salt bridge. So salt bridge is going to have two spectators in it. So we have the K plus and NO3 minus in it. And this is just going to allow so we don't have a buildup of electrons at either of ions at either, right? We don't want too many positive ions at the anode or too many negative ions at the cathode to allow this circuit to flow. Right? You remove any of these parts, you break the circuit, much like switching off your light bulb or switching off your phone, you stop that reaction from happening. All right, so anode, oxidation half reaction. So with this one, we have our zinc, solid zinc's going to the Zn2 plus 2 electrons. So this is the reaction that's happening at our anode, right? It's starting out with a solid zinc and it's losing mass. The solid zinc's going to Zn2 plus and 2 electrons. So the 2 plus is being, you can think of the metal actually degrading or like almost like flaking away. And then you'll have the Zn2 plus going to the solution, right? So the metal is turning into zinc ions. So metal atoms are changed to positive ions. The metal dissolves and the anode loses mass as the cell operates. All right, so here's our cathode reaction. So this is the reduction half reaction, just like you'd see it in the table. So you're going from the ions, U2 plus 2 electrons, to solid copper. So in this one, the positive ions are being changed into metal atoms. So you're taking those ions from solution and you're actually plating them right onto the cathode. So the cathode is gaining mass as the cell operates. Our flow of electrons. Electrons flow from anode to cathode through the wire. It's a conducting solid. So remembering the flow of electrons, that's important. You're always going to ask where it flows. I just remember it flows in alphabetical order. A to C flows from anode to cathode through the wire. So that's your direction of flow for your electrons. All right, so with this one, we have their anodes. This was in the previous one, zinc anode, copper cathode. The electrons are going to flow from your anode to your cathode. And this is a voltmeter. This would be something that you would check the voltage of the cell. So how much potential you're going through the wire. All right, so remember the anode loses electrons. That's our Leo. Losing electrons is oxidation at the anode. So Leo. So we just added another little letter onto that if that helps you. The cathode gains electrons. So you go Gurk. Leo goes Gurk. All right, so if that helps you to memorize it, that's how you can memorize the flow in our electrochemical cells. So losing electrons is oxidation at the anode. Gaining electrons is reduction at the cathode. All right, so our salt bridge, this is to prevent the buildup of ions at the anode or cathode. So with this one here, so this is they call it a U-tube. So you suspend it in both of the solutions. So look at the other picture. Porous barrier. If we did this lab in class, we'd probably use like a cotton ball or a semi-permeable membrane or something to that. So which the ions can pass through. In the salt bridge, the cations or positive ions go through to the cathode. Anions or negative ions go towards the anode. It's almost like it's quite the coincidence, isn't it? Right? Cations to the cathode, anions to the anode. All right, so that's how they're flowing in the salt bridge. So you should also know the direction of flow. So again, positive ions. So our positive potassium ion goes towards the cathode. Negative NO3 minus ion, our anion goes towards the anode. All right, so we want to identify which metal is the anode and which is the cathode. So you'll have some of these questions in your homework and on tests and quizzes. You have to find out which one is the anode, which one is the cathode, so you can figure out everything else. So that's usually what I do first in finding it. So it's very easy. So the half reaction with the greater potential or the oxidizing agent, the one with the stronger oxidizing agent, the greater potential to be reduced is higher on the table. Right? So that is a cathode. So whatever one is higher on the table, that is your cathode. So just look at your table. If it's higher, it's the cathode. That's the reduction reaction. That's exactly like we see it on the. That's exactly how we see it on your standard reduction table. The lower reaction, so this is a reducing agent, is the oxidation reaction. This occurs at the anode. So whatever's lower on the table, this is going to occur at the anode. So this is what's happening for our electrochemical cells. It'll be different later, but when for non-spontaneous reactions. But these ones are all spontaneous reactions. Higher is the cathode, lower is the anode. All right, so here's some examples of electrochemical cells, right? So you should know these pictures of them and what's happening at each of them. So these are all different pictures that you might have on tests and quizzes. So we have one's the anode, one's the cathode. You have your salt bridge. In this one here, you're going to have a porous barrier. Sometimes you might have a gas being injected, and so then you have the reaction happening at the anode. So in this one here, we have a platinum electrode. So this is a so this would be a non-reactive electrode, the platinum electrode. And you can see this one here, also a platinum electrode. You might have carbon rods as inert or non-reactive electrodes as well. All right, so be familiar with these guys. Here's some questions from your book. I suggest doing as many as you can as time will allow. And just to find out the different parts of your electrochemical cell. Ask questions in the chat if you haven't. Okay, so this next one is on standard reduction potentials and voltages. So we're going to be talking about how much voltage would be produced if you hook up two half cells. So the voltage, this is the tendency for electrons to flow in the electrochemical cell. Reduction potential of the half cell, so this tendency of a half cell to be reduced or take electrons. Our voltage, this is the difference in potentials of the two half cells. So you hook them together and then you find out their different potentials, and then you find the voltage flowing through the wire. So these ones on your table, take out your table if you don't have it, the standard reduction potentials of half cells. So it'll have numbers. This is the last column. So positive numbers at the top, and then you see they go to negative numbers as they go down. So the half cell potential can only be determined by connecting with another half cell and reading the voltage. You can say that this is the same as the ability of a soccer team can only be known when it plays other teams, right? You can practice all you want, but you don't know how good you are until you actually play teams. And your potential can change depending on the team you play. So, for example, if we had a high school soccer team play against a middle school soccer team, right? The high school soccer team is going to have higher potential than the middle school soccer team. Just like the high school soccer team would have a lower potential if they played against a team in, say, like the Premier League, right? So much lower potential than they would against a Premier team. So it depends how good you are, depending on who you play, and then you can get your potential from that. So similar things were done when finding the potentials of these half cells. So a standard half cell is used to complete other half cells. So standard conditions, this is 25 degrees Celsius, 101.3 kilopascals or 1 atmosphere. So it's all at standard potentials. That's what this little dot means beside the E. So the E naught, they call it. This is mean it's all standardized. So everything is standardized. So if you look at the back page there, it's all 1 molar concentrations, 25 degrees Celsius. So everything's at standard conditions. If you change the concentration or you change the temperature, you're going to be changing things around like everything else. So these are all at standard conditions. And at standard conditions, the H2 half cell was assigned the reduction potential of 0.000, right? So if you look on your table, you see the potential of hydrogen is 0. That's just because they made the standard was hydrogen and they just hooked up everything to hydrogen. So it's their potential relative to hydrogen. All right, so hydrogen is the standard and everything else is varied with that. Right, so yeah, so this is, so if you look at the bottom here, so acts as an anode or cathode. So again, everything's just standardized to our hydrogen. All right, let's go on to some questions actually calculating the voltage. So when you're looking at it, using reduction table to find out the initial voltage of electrochemical cells. So first, you have the half cell. So the higher metal on the reduction table is a cathode. The cathode half reaction on the table. So you just write the electron potential as you see it. So exactly how you see it on the table, that's how you're writing it for the cathode. The anode is a reverse reaction. It's the oxidation reaction. You write it backwards and you reverse the sign of the electron potential. So if it was plus 0.45, then it's going to be minus 0.45 if it's oxidation. All right. Reduction, you write it exactly the same. Oxidation, you reverse the sign. Multiply the half reactions to cancel out the electrons, much like what you did with balancing the whole redox reactions. You want there to be no electrons in the whole reaction. So most of the electrons are at 2 electrons, you notice on your table, but you do have some that are 1, some that are 4, some that are 3. Whatever they are, you just want to balance them out so the electrons cancel out. So if electrons on one side, electrons on another side, you want to multiply so that you get rid of the electrons in the overall equation. Don't multiply the electron potential values. All right, so that's already taken care of. Don't multiply the values, just multiply so that you have everything is the same on the left and on the right of the equation. Add up the half reactions, get the overall redox reaction, and then add up the electron potentials to get the initial cell voltage of the cell. And that can find out what potential your half cell will have. So this would be the same as having a fully charged battery. So it's the most that you could have, the greatest potential that you could have in the cell. A dead battery would be at equilibrium. We'll talk about that later on. Okay, so consider this one. A cell is made up of nickel, Ni with 1 molar NiNO3. So you're going to have Ni2 plus in the solution. And then you have another one, Fe with 1 molar FeNO3. So you're going to have Fe2 plus in it. So you have Ni and Fe. So basically what you want to do is write the cathode half reaction with electron potential. So look on your table, which one's higher? All right, so I see Fe going to Fe2 plus, negative 0.45, and I see my Ni negative 0.26. So that means my nickel, it's higher, so it's my cathode. So I'm going to write out the cathode reaction exactly how I see it on the table, right? So Ni plus 2 electrons goes at negative 0.26. So my anode is the Fe. So Fe, I'm going to write it exactly backwards. So we're going Fe2 plus 2 electrons, and I'm going to change my sign. Notice how on the table it's negative 0.45. Now it's going to be positive 0.45. All right. So overall balance reaction, notice how electrons, we got 2 electrons and 2 electrons, so they're just going to cancel on both sides. So it's going to be Fe plus Ni2 plus goes to Fe2 plus and Ni. Balance of charge, balance of atoms on both sides. Add up these ones, negative 0.26 plus positive 0.45, and that will be equal to positive 0.19. So that's the potential that's the highest potential that we're going to get at standard conditions with the cell, right? So that's like the fully charged battery. So at 0.19, so that's the most we're going to get. So our initial cell voltage, 0.19 volts. Okay, so here's another question. These are examples of like maybe test questions or something like that. So maybe I'll do these ones. I'll do these ones with you. I'll do this one with you, and then I'll let you try the other ones. All right. So we have metal X. So we don't know what metal X. We can see our last one is named the actual metal X. So we're gonna use all the information to determine what our metal X is, and we have X. X solution in here. We see we have the electron flow, our electrons flowing from this to that. So right away, we know that metal X is our anode and this metal chromium is our cathode. So I would write this stuff right away. So we have, this is our anode and this is our cathode, right? Remember, electrons go from anode to cathode through the wire. Our initial cell voltage is 0.45. So that will come into play later on. So write the equation taking place at the anode, include the electron potential. So the one taking place at the anodes, we don't know the electron potential yet, but we can find it out. We can find it out later. So equation happening at the cathode. So we're going Cr3 plus 3 electrons is going to go to our solid chromium metal. And our electron potential for this one at our cathode, negative 0.74. All right, so since this is negative 0.74, we can, and we know our initial cell voltage is 0.45, right? We can find out the voltage for our metal X. So determine the reduction potential of your X2 ion. So this must be negative 1.19, the reduction potential. And so it's positive 1.19 for our oxidation potential. Towards what beaker do the NO3 minus ions migrate? All right. So NO3 minus, these are anions, so they're going to go towards the anode. And the actual metal here is our Mn, and this is going to be at negative 1.19 volts. All right, so here's another one. Try these guys out. I'm not going to go through all of these, but I do have. But if you look on your PowerPoint, you can see all of the problem, all the answers, and I'll show the answers on this one. I'm just not going to go through them. All right, but it's the same sort of thing. You have the electron flow going from this one to that one. So we know this is the anode, this is the cathode, right? We initial cell voltage. So it's very similar. These guys just take a little bit of practice, but then once you get a hang of it, they're not so bad. So here's the answers to this one. All right. And our next one, very similar, a little bit different. This isn't giving us the, this one's not giving us the electron flow, so we'll have to do that later. All right, here's our answers for these ones. And okay, so this next one is voltages at non-standard conditions. So when the cells are first constructed, not at equilibrium. So when you charge your battery, it's not at equilibrium. A dead battery is when it is at equilibrium. It's all spent, right? So for the cell, so we have a cathode half reaction, anode half reaction for this half cell. So this is, you may see this type of cell notation on problems from your book or whatever. So you have the solution, the metal, it's connected, and then the other metal connected through the wire, then the other metal and the other solution. So this is the cathode half reaction, anode half reaction, higher the cathode, lowers the anode. And then we have our initial cell voltage 1.10. All right, so just like we were doing in the previous section. So electrochemical cells are exothermic, right? They give off energy, right? If you have a battery, you've been using it, you touch it and it's hot, right? Your phone, you've been using it a lot, it's hot. That's because it's giving off energy as it makes that chemical energy to electrical energy. All right, so this is what it looks like. So initially we have CO2 plus, we have our reactants and our products and energy. All right, so as the cell operates, our Cu2 plus concentration goes down, right? And our Zn2 plus concentration goes up. Reaction shifts left, and our voltage is going to decrease, right? So eventually these tendencies become equal. Cell has reached equilibrium and the voltage is at 0.00. So you might come across questions like this on your assignments or tests. You have the cell voltage is at 0.00, it's at equilibrium. All right, so if the cell's discharge, it's at equilibrium, and so that's it, right? It's just asking your ideas about the equilibrium. All right, so let's talk about this one. All right, so initial cell voltage, we got equilibrium cell voltage. So they're going to get, so on some questions, they give you a cell and they're asking the equilibrium cell voltage is this and or the initial cell voltage. Equilibrium cell voltage is always 0. All right. So your battery is always going to discharge. You leave your phone uncharged. So you leave your phone in your closet for whatever years. It's an old phone. You turn it on, the battery's dead. You have to recharge it, right? It's going to steadily discharge as time progresses. All right, so we have this one here. So this is our reaction, right? So our initial cell voltage is 0.29, right? We have, so what's going to happen to the voltage when we add more CrNO3? So that's adding more Cr3 plus. All right, so then we're all the way back to Le Chatelier's principle. Add more Cr3 plus, this concentration increases, then we're going to shift left. So shift left means we're going to have less energy. So the voltage, the Cr3 plus concentration is going to increase, and our voltage will decrease. All right, so increase Fe2 plus, increase Fe2 plus, we're going to shift right. So that means our voltage is going to increase. Add a different solution which precipitates Fe2 plus. So precipitating Fe2 plus, that means this concentration is going to go down. So we're going to shift left. So Fe2 plus decreases and voltage then is going to decrease. Cr3 plus is removed by precipitation. So we're taking away this one. So we take away this one, we're going to shift right. So that means our voltage is going to increase. Increase the surface area of the Fe electron. The voltage doesn't change. Surface area doesn't change. It will just make the reaction happen faster, right? But we're going to have no shift, just like in every other Le Chatelier's problem. Salt bridge is removed. So if salt bridge is removed, you've taken a critical part of the battery out, and so voltage will decrease. If you're doing this, it's going to stop the flow of electrons. All right, you have to have that complete circuit in order to have the flow of electrons. All right, so comment about activation energy. Even if our electron potential is positive, not all redox reactions are spontaneous. Sometimes you need a little bit of something to get them going. So I can think about situations where my batteries were too cold, right? So you're taking pictures, your battery's too cold and camera doesn't work or something like that. So sometimes you need to warm up your battery in order for it to get going. So that's just your activation energy. So sometimes your potential's lower than what you think. Comment about surface area of an electrode has no effect on the cell potential since the concentration of a solid is constant. Increasing the surface area will increase the reaction rate, but it does not increase the overall cell voltage. Increasing the surface area will increase the length of time the cell can operate due to increased reactant material, right? Again, but it has no effect on the cell voltage. Right? Comment about half cells which are not at standard conditions. So half cell is not at equilibrium. If the battery is discharged, that is at equilibrium. Increase in temperature, concentration, or pressure will cause the equilibrium to be shifted. Thus, the system can no longer be at standard state. So you no longer have that little dot And so it's no longer standard electron potentials. All right. So must be at standard potentials for our voltage readings to be true. All right. So here's homework from your book. Do as many as you can, and questions in the chat if you have them.